Yes, you can start.
Okay, hello everyone. I will be presenting the paper Multi-Stage Spectral Wise Transformer for Efficient Spectral Reconstruction. This work was a winner at the Spectral Reconstruction Challenge 2022. Here you can see the link of the GitHub code and the paper and also the dataset. Actually, Hyperspectral images, or HSI, captures the spectral information of a sense across multiple wavelengths and make it more richer than the regular RGB images. HSI has different application in a different fields like the medical imaging, remote sensing, and environmental monitoring. Um, Traditional methods for HSI actually needs hardware and also they are time intensive, which limits their usage in different real-time scenarios. This work aims to generate high quality HSI from the RGB images. Current approaches using like the convolutional neural network CNN, they perform well, but they face different challenges. For example, they struggle with the model long range dependency, and also they fail to effectively capture self-similarity with the spectral data. In order to address this limitation, the author of this paper used a transformer-based framework for spectral reconstruction. Here you can see the pipeline of the MST++ model architecture. I will explain all of these steps. MST is a multi-stage spectral Wise transformer. SST is a single-stage spectral Wise transformer. SAB is a spectral Wise attention block. FFN is feed-forward network, and SMSA is a spectral Wise multi-head self-attention. For the first part, MST multi-stage spectral Wise transformer MST++ is a cascade of the NS single stage spectral Wise transformer, which takes the RGB images and then as an input and reconstruct the HSI images. SST, it's like the U-shape single stage spectral Wise transformer, consists of the encoder, decoder, and also the bottleneck. The embedding and also mapping block are a single convolutional 3x3 layers, as I explained. The feature map in the encoder sequentially take part in a downsampling operation, which is a stride conv 4x4 layers. And then one N1 SAB, and then downsampling and N2 SAB. The bottleneck is N3 SAB. The decoder employs a symmetric architecture. The upsampling operation is a stride deconvolution 2x2 layers, and the same as the symmetric architecture. SIB is here. It consists of the two FFN and also SMSA. FNN is here. It consists of these two and also two normalization layers. And about the SMSA, which is the most important part of this paper. Here, actually, input feature map X actually has dimension h by w by c, where h and w are a spatial dimension, as you can see here, and c is the number of the spectral channels. X is reshaped into a tensor of the size h w by c, which is a spectral c is a spectral channel as a dimension. X is projected to three components: Q, query, K, key as a K, and V as a value matrix, which using learnable weight matrix. Q and K and V have different, they have a dimension HW by C. The spectral dimension C is divided into n smaller chunk, they call it head, allowing the mechanism to learn multiple attention patterns. But here is one by one, as you can see in the pictures. For each head, the attention is computed using the dot product between Q and K. A is the attention matrix capturing dependency across a spectral channel, and the attention matrix is applied to V to generate the output for each head. And the output of the all head are concatenated and passed through a final layer projection to the product output. And V is a weight matrix for the output projection, and to incorporate the positional information here, information of the spectral channel, a positional embedding is added to the final layer. And you can see here output with the H, W, and C. The data set that they used is ARAD1K, that this data set provided by a spectral reconstruction challenge, and it has like 1,000 images, RGB HSI pair images. This data set is split to the train, validation, and test. The size of each of them is 482 by 512, and it has 31 wavelets from 400 to 700. 950 images is in the like the train and validation, and 50 which they have like the RGB image and HSI images, and we have like 50 image in the test set. They are just RGB images. And as you can see here, these images, this data set actually available with the 31 channel and also 16 channel. In order to run these inferences, we need the environment with the Python tree and NVIDIA GPU and CUDA, and also like the Python package that all of them are in the requirement file. In order to prepare the data, we need to have like the training spectral image and the training RGB image in one folder, and then validation spectral and validation RGB in the other folder, and test RGB in the separate folders. And here you can see the directory of the data set that we need to inference this actually model. In this paper, they tried a different method, as you can see here. And I tried HSCNN plus and also MST++. Here you can see the architecture, the code of this MST++, as I explained from that plot or graph. They implemented all of these parts, like the having like feed forward, and then encoder, a bottleneck, decoder, and then projection, the embedding, they implemented all of these parts in this code. And here you can see the summary of the model. Yeah. And then, as I explained, I tried the two models. The other is HSCNN plus, and here is the code of this model, and here is the summary of the model. And then here I tried to evaluate on the test set. We need to download the pre-trained models and put in a specific folder, as I mentioned here, and then try to test on the transformer model, which is MST++. We need to set the data set and then define which model we will use, and also the path of the model, and also the output and how many GPU we will use. As you can see here, this files loaded. I mean, this are actually RGB images, and then the reconstructed images generated in this folder in this path. And here is testing with the CNN Plus model. And the same they generated in, created and generated in these folders. In order to see how is this result, I have selected one images, as you can see, and then selected the which MST++ model. And then by running these parts, this cell, you can reconstruct the hyperspectral image of these images in these folders. And here is with the HSCNN plus, and here you can see the visualization of this generated images. Yeah, this is with the 16 band spectral, and this is with all the band. You can see the difference. And here, in order to evaluate how this model perform, they tried with the validation set, and here is the testing with the MST plus. Here, all of these images loaded, and as you can see here, there are different MRAE and RMSE and also PSNR. And with the HSCNN plus, and I have tried one more model, HDNet, and all of them here you can see the different metrics. And this is the result. I mean, they have used different methods, and this figure shows FLOPS, params, and PSNR that actually it's like comparison with other spectral reconstruction algorithm. FLOPS is floating point operation per second that shows the computational complexity, and PCNR is a peak signal to noise ratio, which shows the performance. And each of these single circles shows the memory cost. And as you can see, MST++ has the highest PCNR and the lowest FLOPS and the lower memory actually. And in order to compare with the other methods, as you can see on the validation set, according to different like the metrics and with the different methods, MST has like PCNR 34, yeah, here, and also it shows that improve over previous methods. And in terms of the efficiency, it's required 23.05 FLOPS, which make it like a lightweight model. And also MST Plus has a lower error rate. I mean, RMSE is the root mean square error, and MRAA is the mean relative absolute error. As you can see here is the lowest. And in general, the data set for evaluation consists of the RGB and HSI pair with 31 spectral band. And for the quantitative results, MST++ outperform all other models in metrics like PCNR, RMSE, and MRAE. And for qualitative result, a visual comparison shows that the MST Plus produce a sharper and more detailed hyperspectral reconstruction with fewer artifacts, and it excel in preserving a spatial smoothness and restoring a spatial consistency. Yes, this is the
Yeah.
whole part.
Okay. Thank you. I stopped the recording.
Yeah.
Let's just.
Um,
Mm,
and then